you can see this, right?
Mm-hmm.
So, um, for
Was there
question
any
number
reason, sorry, was there any reason that you like chose to start with this, with
one,
solutions in electrochemistry?
so I've um done like I have the UWorld course, like the video course,
Yeah.
and I've done like a full pass of chemistry with like Chad's prep, like just the video series, and I realized like I just don't under I didn't understand like the solutions and buffers, so I like watched the videos on UWorld, took my own notes, and then I was okay. I think I can try to at least attempt these questions. That was it. And then I know that it's pretty high yield, so I was like, let me just spend a little bit of time on this and see.
Mm-hmm. Okay. So I guess like before we like go into this, like what like does the actual like conceptual like material make sense? Like because like this is kind of like what I was saying about like that like wanting to like dive into not necessarily dive into UWorld because it may like let's say that there's like a really simple like electrochemistry question that you wouldn't understand. Well, all right, let's just have you I guess like tell me like stuff about this topic. Um
Okay.
yeah.
So I know what you mean. Like, is it a conceptual problem? Is it a conceptual like issue? Is it like a processing of the question issue? Is it, like all the above? I know that when it comes to like electrochemistry, there are two different types of cells, electrochemical cells, or aka like galvanic cells, and then electrolytic cells.
So let's go
Uh,
like from bottom up kind of
mhm,
thinking. So instead of starting with like the different types of electrochemical cells, it all starts from the concept of redox,
mhm.
right? And like one way to like be able to tell if you're thinking of something like in that foundational way would be like, okay, can you have redox without electrochemistry? Yeah, it happens all the time, but can you have electrochemistry without redox? No, not ever. So, um, so yeah, like galvanic, sure, but start with redox. Just tell me a little bit about that.
Okay, so redox reactions, you can see if something is a redox reaction by looking at um, like a reaction and seeing for each element like its
So let's just
electrons.
let's just talk about what
So,
is it conceptually? Like what is redox?
like a gain or loss of electrons.
Okay, so since you're going to have like things are going to be conserved, right? Redox is really just a combination of what two things?
Reduction and oxidation.
All right, tell me about those.
So in reduction, your a substance can either be so reduction is where you're going to gain electrons, but I know there's a difference between like something being like a reducing agent and doing reduction, and then oxidation is losing electrons, but it can also vary if something is like an oxidating agent, right?
Yes, so redox will require both of them to happen. Like you can't
Mhm.
just have oxidation, you can't just have reduction. So the reducing agent, since it ends in ing, that means that it's doing it as a verb.
Mhm.
And so if it's reducing something else, it itself gets oxidized, right? Okay.
Correct.
So uh, so that's the fundamental kind of principle that people eventually were smart enough to take advantage of in order to generate electricity, right?
Mhm.
So okay, so um okay, so tell me about galvanic cell or
So I know that for galvanic cells, you don't necessarily need is it like a battery to um do like its main function, and like the anode is mostly like on the left hand side and the cathode is on the right hand side.
so right and left are arbitrary, but anode, um, so like I remember like in high school or something, I don't know if you learned it this way, but whoops. Oh yeah. Red cat
Hmm.
and whoops. And anox, right?
Hmm.
So this just means that the definition of a cathode, right, is something that gets reduced. And then the definition of an anode is something that gets oxidized. And so this means like this is true all the time. So it doesn't matter if something's on the left or the right or anything like that. Um, that's you'll always have reduction at the cathode, you'll always have oxidation at the anode. Now, I just drew like a regular battery here because it's a lot more intuitive than like the weird like two-beaker thing they usually draw.
Hmm.
But so like on in a regular battery, like down here, let's just say is like the negative end, over here is the positive end, and then like okay, like what does that mean? It's just like let's say like the lithium ion battery like in your computer or in your phone, lithium
Hmm.
is going to be like a positively charged ion, so that can also be called so a galvanic cell, like I'll write it down, but there's really only two types, right?
Hmm.
Meaning a galvanic cell is essentially the same thing as an electrochemical cell, which is the same thing as a voltaic cell, which is pretty much the same thing as a concentration cell. Um, it's just that a concentration cell uh, does not need to use two different materials. It could just use one. So like the lithium ion batteries, like you'll have a high concentration of lithium ions up here where I wrote positive and low concentration and on the bottom end here. And now what do you think this top part would be? Um, the anode or the cathode?
So I know that from um are we talking about just like based on the flow of electrons? Like, wouldn't electrons be moving from the positive end to the negative end? So, if that was the case, this is going to be like the
So
um.
so if you had a positive, so if you had okay, so if you so like charges repel, right?
Mhm.
So would it make sense for electrons to come from the positive end?
No.
Correct. Good. So, and this is just, the basic kind of principle of like also like equilibrium in a sense, like not the same equilibrium that you see in like solution chemistry and stuff, but everything wants to ultimately become neutral, right? So the side that has um, more positive ions will, by definition, have fewer electrons.
Mhm.
And the side that has, we'll say like the negative end will have more of an abundance of electrons. And and so I drew this impermeable like membrane here.
Mhm.
And that means that, they can't travel through it. But if you connect like a copper wire or, a conductor or something like that between these ends, you're going to have electrons flowing from your negative end to your positive end, right? So now, so okay. So which side would be the anode? Which side would be the cathode?
So naturally, since electrons are going to be flowing to the positive end, right, it's going to be gaining electrons. So it's going to be the cathode,
Hmm.
right? The negative end, because it's losing, because it's the electrons are leaving, it's going to be the anode.
Hmm. Very good. Very good. So now, what this means is that we are taking advantage of redox, which you can classify as a chemical reaction, or let's just say chemical energy, and
Hmm.
we're um, translating that into electrical energy, right? And this is happening. So this is like essentially a way to generate energy. Um, it itself is generating the energy. We don't have to do anything about that.
Hmm.
So we can say that it's a spontaneous reaction,
Yep.
right? And when they talk about um redox, they'll oftentimes give you like a reduction potential, like half reaction
Huh.
chart or table rather. And just by convention, like since reduction is, gain of electrons, like let's say we have like, okay, like A plus like some element plus an electron gives us like I don't know, I'll say like solid,
Hmm.
and I'll do another one, and then they'll give you like their reduction
Reduction.
potentials. So let's just say we have like 1 and 3. I mean, like, usually it'll be like point something like that. But from this table right here, um, so if we constructed like an electrochemical cell or something like that using these two materials,
Hmm.
um, since the reduction half reaction is just showing us reduction, one of them has to be oxidized. Which one do you think would end up being?
Being
Yeah.
oxidized.
Hmm.
So obviously you compare, yes, because I know like the E cell is like the sum of you know, the reduction and the oxidation. So the one that's more like the highest number would be the reaction that's doing the reduction, and then naturally the opposite. So like the first one, A plus electron is, this one right here would be the one that would have a higher oxidation number, right?
So you're saying that this one would not get reduced, right?
Right,
Good. Good, good, good. So then what we can do is we can just draw it with an arrow going backwards, and then we just flip the sign.
correct,
And then you can add them to get your overall cell potential.
correct.
And then with this,
Yep, that
there's a
equation.
negative there. Yeah,
Right.
there's a negative there. Um, uh, but yeah, so that would mean that okay, so yes, in your electrochemical cell, that's what's going to happen. So it's a way for us to generate electrical energy by taking advantage of a separation of charge. Now, eventually, this is going to like enough electrons will have reached the positive end to make it neutral, and enough have left the negative end to make that neutral, so that this is a dead battery now.
Hmm.
So what we can do now is we can plug it in to an external source of electricity,
Hmm.
and this external source is essentially going to be like the galvanic cell being forced to run in reverse.
Okay, so it would be going back to the anode.
Yeah. And since we are forcing it to go in reverse, we would want the signs to flip, right? So now your anode end, right, is going to be positively charged. And this is momentary, like, but this is a way for you to make two like important distinctions. Like one, you can't like define an anode or cathode by its charge alone, and then two, if this is gaining electrons, like the bottom end,
Hmm.
would that mean that it's no longer an anode? The answer is it won't mean that it's no longer an anode because it's not get like even though it's gaining electrons, it's not gaining electrons from something that's getting reduced.
Hmm.
So the entire idea of anode and cathode uh is based on um the fact that they must be in a pair.
Okay.
So okay, so now electrons are gonna like flood to like the anode end, and that's a way for us to recharge it to recreate that charge separation, which then means we can, unplug it and then use it as a battery again.
Hmm.
So now you could think of this as using electrical energy to
Okay.
convert into chemical energy.
And
And
that's essentially
yep.
what like that's like the I don't know if this is like a main differentiation between this and like a electrolytic cell, right? Because that's why like the delta G is it's would be like a non-spontaneous reaction, right? Like
Yes.
it's the whole okay.
So yeah, so we are forcing, so it's not spontaneous, um, and electricity to recreate that charge separation, and that will be your electrolytic cell. And the most common, like I think most intuitive way of thinking of it is just essentially like chart recharging a battery. But there's going to be two other uses for it. One being like electroplating,
Hmm.
like if you had like an aluminum like I don't know like spoon or something like that, and you want uh to coat it in like silver, that could be one of the uses. And then the other use is where the word electrolysis comes from. Like if you've ever wondered like, hey, how do people breathe in a submarine?
Hmm.
Well, they take the water that's around them and they subject it to electrolysis to separate H2 gas from O2, and then
Hmm.
they could just breathe that. So, but another, I guess, good way to think about it is an electrolytic cell will require an external source of electricity or an external source of energy. So so it's like going to be plugged in. It could even be plugged into a battery,
Hmm.
right, itself. So okay, good, good, good. So that's pretty much electrochemistry. I'm trying to think if there's anything else, but yeah, that's pretty much it. Any questions?
No, so like the delta G is equal to negative nFEcell. So then N is this is where we get like the ice table from, or is this like a constant? I know F is Faraday's constant, E cell is, you find that based on, like the summation of the redox potential and the oxidation potential. But what was N? Like I'm blanking.
Got
Where
it.
we
So N is going to be your moles of electrons,
hmm.
and like that would be like, let's say this is like B2 plus two electrons, right?
Right.
So that'll just be the number of electrons that are actually transferred in the said redox reaction.
Okay.
And then F is Faraday's constant, and yeah, that's pretty much it. Oh, and your delta G. So if you think about it, your cell overall cell potential, if it's positive, this
Hmm.
entire expression becomes negative, and if you have
Right.
negative delta G, that means it's spontaneous.
Hmm.
And then if your cell potential is negative, the negatives cancel. It'll be positive delta G, and that will be non-spontaneous.
Right.
Cool. All right. Anything else for like from here?
Um, I'm gonna be honest, I feel like my math is so weak. Finding like the pH, like log, like could we could you give me like a dummies course on like setting up like the log equations and like
Mm-hmm.
uh natural logs and like how to do like that mental math? Like I tried finding videos, but I don't think I've had enough time to like really like watch them.
Okay.
So,
So let's think about why do we even like use logarithms?
mhm.
So let's say that we have some situation where we have an exponential curve, like a curve of some sort, and there, what a curve would do would just like kind of like just go up really, really fast. Like its slope would go up really, really, really fast, in a very, very tight range, and that's hard to like deal with. So uh, there's two things that I guess you could do. Like one is, like Michaelis Menten, like in biochem.
Yeah, I've seen the equation.
So like that's also going to be like a curve.
Mm-hmm.
Um, and then there's something called a Lineweaver-Burke plot,
Mm-hmm.
which
Also
is
remember that like enzyme kinetics and
yep. And so that's just it's a double reciprocal plot, and that's just their way of making something that would otherwise appear as a curve uh
mm-hmm.
look like a straight line. And that's what we could do with logarithms as well. We can take, this and, insane, like, you know, I don't want to say spike because that would be like straight, but yeah, this tremendous increase in this y-axis that's over a very, very small and like hard to like measure kind of range here.
Mm-hmm.
It could just turn it into a straight line, right? So, okay. So now you're talking about logs. So like let's actually do a little bit of like okay, so like if I multiplied x to the a power by
Mm-hmm.
x to the b power, what would we end up doing with the exponents?
Right. Well, because like the base is the same, like with both x, you could just add a plus b, right?
Good, good, good. And so now if you're dividing, you would subtract them. And then if you take an exponent to the power of another exponent, you would multiply them, right?
Yeah.
And
That I'm
now
good with. The
yep,
other,
yep, yep. So now logarithm is just a way to reverse an exponent,
yeah.
right? So um okay, so let's say that we had, let's see, like log of, or let's say we wanted to take the log of this,
Mm-hmm.
we would just end up then adding like you would end up you would kind of get rid of the x and you'd be left with the exponents. So this would just end up being the sum of the logs of the exponents, right?
So are we assuming we're putting it in that way because are we assuming the base is 10 or like
Yes. So for the um MCAT,
mm-hmm.
like the default base for log is 10.
Okay.
For like computer science, it's 2, and natural log is really log with a base of Euler's number.
Mm-hmm.
Um, but yeah, logarithm on this test is going to be by default with a base of 10.
Okay.
Okay. Now, um okay, I guess tell me more about what you were
Um,
oh, yeah, with
let's say, for example, we're trying to do trying to find out, let me see if I can find like the actual thing. Like you have to find like Ksp, but um yeah, like this like finding like the concentration of hydroxide ions or like hydronium ions from a Ksp. How would that make sense? Like I have one question. Hold on, let me see if I can pull it up really quick. It's on the other question set, but probably pull it up. Oh, but don't judge me on my scores because they're terrible. So
No, of course not. I mean, it's not even like what's
like
important at this point.
yeah,
Most important thing is that you learn, right?
yeah. Well,
Hmm.
I'm sure we can all learn a couple of things. Let me see. This is question 46. Are you seeing this?
Mm-hmm.
Yeah, so um finding like the Ksp, the solubility constant. What I did, I set it up as Ksp is equal to like the concentration of M2 plus times the concentration of OH minus to the second power. Set it up as POH is equal to the negative log of the concentration of OH minus. I put in 4 is equal to the negative log of OH minus. And then but I don't understand the math on why they're putting it like concentration of OH minus is equal to 10 to the minus POH. And then I guess I don't understand like
So
why.
that's just uh the reverse. Like for instance, if you're so like if they get let's say like all right, we're given pH of 10, what
Mhm.
what your hydronium concentration will end up being is just 10 to the power of negative pH, right?
Right, because I know that pH is the concentration of hydronium ions, so it would make sense that that's what it
Yeah,
is,
so
right?
so pH is the negative log of the H plus or hydronium concentration.
Hmm.
So so 10 to the power of negative pH is just a way of uh uh finding what the hydrogen concentration is if you're given pH. And just like if you're given the hydronium ion concentration and you want to find pH, then you'd use this one down here.
Hmm.
So um so yeah, does that your question or
Yes, that makes sense. Like I got up to that point,
Mhm.
but my question was like, um why did they do this part? Like why didn't they multiply this value um in in over here? Like if we could just like go over like this one just like all together because I just don't think I understand like the application of like this math.
Okay. So I guess like starting from up here, tell me like at which point it stopped starting to make sense or felt arbitrary.
Let's see. So I got up to here. Um, I know that they used this value. They looked at the molar ratio, right? 1 mole of M2 is needed to produce like 2 moles of OH minus, which is where they're getting this from. They multiply that together. They got they got this value. But when it came to the KSP, um,
Hmm.
and the 5 to the 10 minus 5 times like this ratio. So I know this is obviously squared because of this, but why wouldn't they have applied like why didn't they just um hmm I guess like this, why didn't they just like multiply this by 2? Because aren't you having like two of the moles of hydroxide here to be applied? Like it would just be like 2 times 10 to the um minus minus 8. Does that make sense? Like why is it being applied here? Or is it because they need to convert this? I don't know
Um,
if I'm making sense.
so you're asking why, like, okay, so you're saying you got this, right?
Right.
And then, like, I guess, and then what they're doing here is where you got.
Yeah, I guess if it was like if it was truly like the concentration of the total concentration of M2 plus we have or I'm sorry, if it was the total concentration of OH, then wouldn't it have been like 1 times 10 to the negative 4 like times 2 and then you would multiply like that mole ratio?
Let me see
Yeah.
the equation up here, so I'll get that ratio. So, okay, so for, 1 mole of this, we have 2 moles of the OH minus, and then 1 mole of the M2 plus. Let me see, an ionic hydroxide compound formed from an unknown metal M exhibits the equilibrium, that, which results in a saturated aqueous solution. And now the word saturated is important to know because so like the entire basis of solubility
Hmm.
is and like what your solubility like KSP like what that represents is the maximum concentration of something that can be like dissolved
Correctly. Yeah.
in a solvent.
Yeah.
And if you go beyond that, you start to get like a precipitate.
Specific. Yep.
Um, you could heat it up and add to it without it turning into a precipitate. That's how you can get something that's super saturated.
Oh, okay.
Um, so okay, saturated. All right, so wherein the molar concentration of M2 plus is half the molar concentration of OH minus. Okay, so now this is um important information that we otherwise would not be able to figure out from the balanced equation. Like the balanced equation will tell you like, a proportion of how they differ. Um,
Hmm.
but which means that you could do your KSP is equal to, this. And if this wasn't like if it wasn't like a solid or a liquid or a pure substance, you would end up, and it was like aqueous or a gas, you would end up putting it as your denominator, right?
Correct. But they only care about the products for KSP.
So all everything that is capital K comes from the
Hmm.
law of mass action, which is
Hmm.
always going to be your, products with, the coefficient turning into an exponent over reactants.
Hmm.
And that's always true. Um, it just it's not like for this. All right, because I could either tell you like, okay, you just ignore it for KSB, but
No,
you
no,
really,
I guess I get it because like as you said, for it's a solubility constant, right? So it doesn't matter what we look at for the reactants because the whole point is how soluble it is. Like so if it's going to be mixed in water, for example, how much is it actually going to dissolve in water? Anything more would be the precipitate.
yeah,
Um,
yeah. So if it's a pure substance, and you just think about, okay, what's the concentration of this pure substance? It's gonna be like 100% what it is, right? So, okay, so we get this over here, and then they're telling us, so we don't know what the values are for these, and like, a lot of times in these questions, like they'll, well, okay, okay. So we don't know the value for concentration of M2 plus. We don't know the value for the concentration of OH minus. And we can't figure that out from the balanced equation. But when they're telling us this, that means that we can figure it out.
Hmm.
So I'm just going to write that. So M2 plus, so they're saying the concentration of M2 plus is half the concentration of OH minus. So this would
Okay.
mean that I could do this, right?
So I have this is maybe that's a silly question, but how is this different from like the number in the front, like the molar like number in the front for the stoichiometric like number to make it balanced?
So the stoichiometric number doesn't give us any information about the actual concentration that's used.
Hmm.
Because you could use, like, let's say for M2 plus, like you could use a concentration of like, I don't know, let's say 50 molar, and then OH minus, you could use a concentration of 1 molar.
Hmm.
The setup is going to not change based on stoichiometric coefficients, but the concentrations can really be anything, right?
Okay.
So, um, okay, but does this make sense?
Yes, but if it's like if it's half of the molar concentration of OH, wouldn't it just be like one half in the front versus two?
Well, so if they're saying that the amount of M2 plus is one half of the concentration of OH minus, yes, you would put the one half on the OH minus side, right?
No, no, I'm saying like for the M2, like
Mhm.
um you put a two in front and why couldn't it just be like one half? Because it literally says like molar concentration of M2 aqueous is half the molar concentration of OH. That means
So
oh that
that would get you this over here. I don't know, it's not letting me right. Okay. That,
hmm.
right?
Okay, so that means that M2 has a okay, I guess I get it. Like M2 has more concentration than OH is what they're just saying that OH is the least concentrated one.
Yep. So so the M2 concentration is equal to half of the concentration of OH minus. So you just take the concentration of OH minus, you take half of it, and that's
Mhm.
equal to the concentration of M2 plus, right?
So M2 plus is two times bigger or two times more than
Hmm.
the
Yeah.
okay.
So that's why I started off writing putting the two there, just because I think it's easier to deal with.
Okay.
So okay, so now this value that we wrote, like M2 plus, in the brackets and stuff, um, we don't need to know what that value is anymore because we were able to make an equation, right?
Hmm.
So I could just now call this X and this X, right?
Okay.
So, and that's something that you end up doing when you do this. Like if you treat this as X, when you do the actual math, I mean, it's a little weird because this ends up being 2x inside the parentheses, but you're still squaring it.
Yeah.
But this will end up getting you 4x cubed, right?
Because there's an X1 times it. Well,
Yep.
wait. Oh yeah, because you're adding them two. Yeah.
Yep, yep. So like yeah, the 2 squared in the parentheses and then x squared and then x squared times x to the first power is x cubed, so that'll be the 4x cubed. And so you're really only going to have three variations of this. You can have x like so if it was like just an equal concentration of both of the things, it would be like x squared. If it was like something has 3 times the amount, it would be 27x to the fourth power.
Where are you getting the three, like the 27? Like, so obviously three times the amount. Wouldn't it just be 3x squared?
So it would be, whoops. Um, oh no, my bad. Sorry. It's from that.
I mean, three times to the third power x, yes, but where are we getting where's the 3x miraculously come? Oh, like you're saying, like if we have three times this amount, like what would it?
Yeah, like so like if you have so like this would be like if m and I'll just call the other thing x are equal amounts, and then for the one where one of them is twice the amount, you end up doing this. And then
Mhm.
what if you had something where it was like that?
Right,
So that's what would ultimately get you like, so this would be x, and then this would be 3x in parentheses cubed,
yep. So
right?
27, yeah, x cubed times x, so 27x to the 4. Yeah.
Yep. Yeah. So that's what you'll get. Um, and meaning the different variations of that. And yeah, and then okay, let's see what they're asking here. If the solution pH is 10, okay, so they're telling us the pH. Now we can, since the pH is negative log of the H plus concentration, if you do the anti-log of that or whatever, multiplied by 10 essentially, you're gonna, that's where you do like, your 10 to the power of negative pH.
Right.
So 10 to the negative 10 is your H plus concentration, right?
Correct.
Okay, now the autoionization of water is the basis of pH because pH is really only used in the context of water. That's why molecules don't have a pH, they have pKa's and stuff like that, right? So, um, so okay, so and then from so we know that if we did this, we would get uh
Mm,
well, 10 to the power of 14 from the autoionization of water.
right.
And
This is just you're rewriting the pH plus POH is equal to 14, right?
yeah. So okay, so if they're asking, let's see. They're asking about the Ksp. Okay. So essentially this means that we can figure out that 10 to the power of negative oh yeah, that should be negative 14. So 10 to the power of um 4 would be your OH minus concentration, right? And then you can plug that in here and then solve for the Ksp, right?
So you're plugging in 10 to the minus 4 and then dividing that by 2 on both sides to get the concentration of M2 plus.
Yeah, I think they're asking us the Ksp, right?
Yep.
So, um, oh. Okay, okay. Sorry. So I wrote it. So it's really going to be like this value. So 2x squared is going to be the 1 times 10 to the negative 4. I think that's what you were, what? Okay. I think that's what I think that's what you were asking me when you asked like why is there that two there?
Right, right, yeah.
Yeah, yeah. So yeah, that's where that comes from.
So you set up the 2x squared equals to like 10 to the minus negative 4
Mm-hmm.
for x squared.
Mm-hmm.
Okay, so if I what would be the math for that? Like if like let's just kind of like look at the right hand side just for an
Mm-hmm.
example. 2x squared is equal to, and so can you write 10 minus 10 to the minus 4 on the right hand side?
Mm-hmm.
So you would divide both sides by 2, or would you yeah, I guess you would divide it, then you would square it. But then what kind of mental math are you doing in your head? Like what's half of 10 to the minus 4? It would just be 10 minus 2.
Okay, so the way that this is not really like the way that I write the exponents. The way that I write it is gonna make it easier in my opinion. So like essentially like a calculator. Like if I wanted to write this, I just write 1e negative 10,
Mm-hmm.
right? And yeah, I would say to like practice thinking of it this way because then that can help you like do the stuff more intuitively. So I'm just going to rewrite this as 1e negative 14, and we divide by 2 on both sides to get 1 over 2.
But why are we getting e to the negative 4? Isn't it negative 4?
Oh, my bad. You're right. Okay. Yep. Yeah, so then we divide by 2 on both sides. And like what helps me is if I'm doing that, I like to write like 2 times 10 to the 0 power
Okay.
because then I can because otherwise I would have to like still have to deal with the exponent part. So this would just be 1/2 times 10 to the, and then it's just negative 4 minus 0, which is negative 4, right? And now 1/2 is just 0.5 times
Mm-hmm.
10 to the negative 4. And now, um, and now I always say this in my head also because it's easy to mess up. So like if I'm making the number on the left larger, like I want to go from 0.5 to 5.
And you would make it smaller.
Well, if I'm going from zero point 0.5 to 5, the number on the left is getting bigger. So I say left add, right subtract. So I'm
Mhm.
going to make the exponent smaller. So 5 left add, right subtract, negative 5. All right.
Yes.
Yep. So maybe that is how we could I mean, like this is just like whatever the concentration here, but so we haven't done the full KSP, but that's like where like the 5 comes from in like these choices, I would guess. Um,
Okay.
and uh, yeah, and then I guess you can show me again like the part where you that step where it stopped making sense.
Well, can I attach like images onto the chat? I just want to show you like my work because
Yep.
I think I was doing something very similar, but
Hmm.
let's see. Um, wait. Is it going to come through? Oh, there we go. Oh, I guess there we go. So I was kind of already doing like I guess I was just doing like an extra step by adding like the one and just trying to make it into like the scientific notation myself.
Okay.
And I So yeah, I guess like my question was like kind of going back like the setup of like the exponents and why do they multiply like why don't they square this ultimately coming from here?
Let's see. So, and then they're multiplying it by,
And then I also see like where I went wrong over here too, kind of like as you were explaining to me, where the two came in for the
yeah, that's a weird one because, um, like you would have to include the two inside of that parentheses as well. Um, but yeah, you basically like I guess the way that they just like that this part's pretty pretty weird. Like, I don't know why they did it that way because moles over liters is just molar, like molarity, right? But
correct.
I think that makes it look confusing, but we ended up getting like the same number, right?
Yeah, and I think honestly that's kind of this is it's easy for me to kind of assume, oh, this is like the stoichiometric ratio, right? Of this because that's kind of how I was approaching it of it too. Um,
Yeah, so what okay, yeah, so we can make a distinction between molar solubility and the solubility product. So your solubility product you can get from your balanced reaction, but your molar solubility, which so when I said the maximum amount that something the maximum concentration of something that could be dissolved in a solvent, like
mhm,
that's literally going to be like the definition of molar solubility. Um, whereas solubility product is, I mean, it's kind of like the same thing, but it's the theoretical aspect of it. So, but when you're dealing with like X values, meaning like molar solubilities, these are not theoretical. These can only be experimentally obtained. So that's why like it's I guess it makes it a little bit more confusing because it happens to like match
right.
it,
Yeah.
or rather not maybe not match it, but like it is a similar ratio, maybe in a different order or a different way like that.
Mhm.
Um, but yeah, ultimately you'll do it, I guess, like the way that you did it on the right, but really just like the way that I did it earlier. um, to get this value, which is going to represent the amount of um, hydroxide ion, right? And then you would um, solve for X, right? And just plug it in to that, right? So you would get this. Because what we were doing was um, the like the 2x squared or yeah, the 2x squared part. We really just solved for x here, and then that's what this is. So um yeah, so this is the x, which is what we solved for here, and then we would put in like that times 2 squared
Mhm.
to get this, or this after you square it, and yep, and then you just multiply them to get your KSP.
Yeah.
So you wrote why didn't multiply here?
Yeah. It's because I just didn't understand the whole concept of this, like that key phrase of like saturated aqueous solution,
Mm-hmm.
where like M2 plus is more in concentration, so it's gonna equal 2 OH. So that's kind of it makes sense why this is that.
Mm-hmm.
Yeah. Okay. And
Yeah,
I need to stop
you're
doing
Yeah, so you're basically so another way that they can ask this is like let's just say that they started with, or we could even do it backwards. So let's say they gave you the KSP of, what was it, to negative four,
Um,
13,
negative
14,
13.
negative 13. Um, and then they could ask you like, okay, what's the pH or, um, what's the molar solubility of hydroxide?
Hmm.
And you would end up, plugging it in here
Yep.
or, setting this equal to the x 2x squared equals 4x cubed. And then you'd solve for x.
Hmm.
But if they asked you, so that x means that, we can then, figure out like the amount or concentration of this or this. And I guess since this one is OH minus, what we solve for, we just do like when we solve for x, we just double it and then we square it, and that gets us our hydroxide concentration, and then we can find our pH that way. So yeah, essentially, um, doing it. I just think like this stuff is makes it very very confusing. I think
Hmm.
that's a problem on their end, but but yeah, that's
Yeah.
the
No, that clears it up.
idea.
Yeah.
Mhm.
And that would make more sense on how to solve it too. So yeah, I appreciate it. This one makes a lot more sense.
Mhm.
Let me see.
I'm gonna use the bathroom real quick. One sec.
Okay.
Okay.
All right, let me see. Question two. What's this? No, I can't even find that question that I was on. Um, but how much time do you have? Because I know we have like 30, but like 20 minutes left, maybe.
Mhm.
Um,
Yep.
Trying to figure out which one was it.
M Catalyst. That's a clever title.
Oh, yeah, not me.
Hmm. Oh, sorry. One sec. I forgot to get water. One sec.
Yeah, it's okay.
Yep.
Yeah, there's so many resources now. He basically just has like this equation sheet where he breaks down like all the equations that he kind of recommends. And so I was like, maybe whenever I have some downtime, I'll just kind of try to memorize, if I can like regurgitate them like on like a sheet of paper. But
So with units, you also want to be able to deconstruct them.
hmm.
So, um, like like a Newton would be, or a good one could be, um, so like we know little g is like 10 meters per second squared, right?
Correct.
Now, and Newton's second law, right?
Yep, mass and acceleration.
Yep. And it gets really like the sum.
Mhm.
So we could also express this as 10 kilograms or 10 newtons per kilogram, right?
Right.
And that is I would say even more of a useful way to understand what this represents because rather than thinking of it as just the acceleration due to gravity, you can consider it the strength of the gravitational field. So what that means is on the surface of the Earth, a 1 kilogram object experiences um a force of 10 newtons.
When you were saying like
Deconstruct.
electric, no, like the electric, you were saying electric field, right?
Like just now or
Yeah, yeah, just now, or was I like did I
oh
mishear
sorry
it?
no I sorry my I meant gravitational. So basically the um yes on the surface of the Earth, so an object, so a 1 kilogram object on the surface of the Earth is in a uniform gravitational field,
Mhm.
and the strength of that uniform gravitational field is 10 newtons per kilogram, meaning that a 1 kilogram object in this gravitational field will experience 10 newtons of force.
Yes, in the downward direction,
Um,
right?
sure, but that's really just thinking about where is that force originating,
From
and gravity exists solely due to mass. And so the Earth has a greater mass than we do. So we would be saying, yeah, it's bringing us down.
hmm
But let's say you're the sun, you're not going to be like, yeah, it's bringing me down. You're going to
Yeah.
be like, it's coming towards me. So, um, yeah. So like that's something. And like for
Okay.
these prefixes and stuff,
Uh-huh.
like you could also kind of think of like how many years are in a millennium, right? And like century.
Yes, common sense.
Or I always say like, which is true, like at least 60% of the English language is based on Greek and Latin roots.
Mhm.
So that's why, it connects. But you could also think about, because I noticed you didn't write anything after mega, but like how much space is on your hard drive?
Mhm.
It's in what? Gigabytes.
Yep.
And and is that would you rather if someone's like, I'm gonna give you like a 100 megabyte hard drive or a 100 gigabyte hard drive, what would you rather have?
Ooh, Shane, you're asking the wrong person. Is it 100 gigabytes?
Yeah, because giga, so
Yeah.
that means giga must be larger than mega.
That
And you
correct. Yeah.
basically go, and if you just think about it, like when let's say we wrote like a number, we put like in regular whatever writing, we put a comma after each like three zeros or three digits rather. So
Okay.
these move in that direction. So 10 to the 6 means million, that's mega. Giga is 10
12 or
to
No,
the
I guess
ninth,
yeah.
because you go by powers of three, right?
Mm-hmm.
And then you can have a terabyte,
Is
one
the 12.
E12,
Um,
and then you can have a petabyte, a yottabyte, and then if you go smaller, so you have your milli, your micro, which is a millionth, nano, a billionth, and then you can also have your pico,
mhm.
which is to the negative 12. And then you can have your femto, which is to the negative 15th, and then your atto, which is negative 18th. You can go even more, but yeah. Yeah. So, yep, for those. But yeah, what I just really want you to be able to do is be flexible with units and be able to deconstruct them and like a joule, and because if you can deconstruct your units, so okay, let's say you don't know the units for something, the formula will help you figure that out. Let's say if you don't remember the formula for something, the units will help you figure it out.
So I know, like, let's say, for example, this, I mean, if you hadn't told me, we just discussed, I'd be like, okay, yeah, Newton's force, kilograms, mass, like, is this something to do with force and,
Well, it's just up here, right? Just
right?
rearrange this so force over mass equals acceleration,
Mm-hmm.
right? Um, and this is true even for this, right?
Yeah.
Well, actually, I should tell you like where this even comes from. So it comes from the universal law of gravitation, right?
Is this different from the center of mass concept?
Well, center of mass is just going to be something about, yeah. So this is like the fundamental thing that brings gravity and force and the fact that it's proportional to mass and inverse square relationship with the radius. So
Mhm.
this entire thing is really just a simplification of this, right? So like for instance, like let's say M1, M2, if we just think of them as like these spheres, like they're gonna, I mean, I could draw like the field here,
Yeah.
but let's say that we want to concentrate, let's say that mass 1 is Earth, and this box here I want to zoom in on so much that we're on the surface of the Earth where it looks like a flat, like it's flat. And let's say this is you. All of these field lines are going to be perpendicular to the surface.
Mhm.
Okay, and which means that it's well, it's also going to be uniform. So if I plugged in, use like a different color. If I plugged in mass of the Earth for M1, radius of the Earth for R, and
Mhm.
then, G over here, this ends up giving you the 10 value or little g. Whoops, little g. So that's where that comes from,
Mhm.
right? And this, if we wanted to do a uniform electric field, this is your, capital E, which is the electric field strength
Mhm.
times, well, it's probably easier to think of it, but this one, right?
Yes, the charge and the electric field strength, yeah.
Yep. So now so what I circled in blue here is the electric field strength, is the capital E.
Oh, so it's like almost like the equivalent of the G, like of what we
Yep.
were explaining before.
Yep. There's literally no difference, besides like, the constant, right? Meaning in the mathematic relationship being based on like 2-point charges or 2-point masses,
Yeah.
right? So that's why um you could also think of electric field as, well, you could do this, right? Which would give you some force in newtons that some 1 Coulomb charge experiences, right? So it's
Mhm.
just like this, but gravity is based on mass and electricity or Coulomb's law, electrostatic force, is based on charge.
Yeah, it's so hard to like wrap your head around it too, because like when you were drawing this, my mind was on, it looks like this is, like positive, negative, like the charges, the direction of the charges, and um, but yeah, like you just have to kind of draw these parallels. Like I just have to make a constant effort to like see, um, instead of like trying to understand rather than memorize.
Exactly, yeah. So and yeah, just being able to be flexible with so like over here, right? It says electric field is volts over meters,
Hmm.
right? So but what is a volt? A volt
Like
is
of a
yeah,
charge, right?
what's
Is
up?
the strength of a certain charge?
Well, when you say strength, right, of a charge, strength just means, I guess, some large number. So strength of a charge will still be a charge, right?
Hmm.
So it'll have to have a unit of Coulomb. Um, but a volt, they also talk about as potential. And they talk about it, they use that word because, well, what's the other thing that we talk about with that word? We talk about potential energy, like specifically like the gravitational potential energy. But voltage is really just like the electrostatic potential energy. So we can think of it. So 1 volt is your energy or work in joules per Coulomb,
Hmm.
right? And so like, and then if you multiplied this by meter, or rather, I guess they're dividing it by meter. But yeah,
Hmm.
essentially just being able to be very, yeah, newtons per Coulomb. That's what I just over here.
Like that derivative. Yeah. Yeah.
So yeah, so like it's better instead of just like having to know this, to see how they're equivalent, like yourself.
All right. Fair
Mhm.
enough.
Yeah.